In computer science, the time complexity of an algorithm quantifies the amount of time taken by an algorithm to run as a function of the length of the string representing the input. The time complexity of an algorithm is commonly expressed using big O notation, which excludes coefficients and lower-order terms. When expressed this way, the time complexity is said to be described asymptotically, that is, as the input size goes to infinity. For example, if the time required by an algorithm on all inputs of size n is at most 5n3 plus 3n, the asymptotic time complexity is O, n3. Time complexity is commonly estimated by counting the number of elementary operations performed by the algorithm, where an elementary operation takes a fixed amount of time to perform. Thus the amount of time taken and the number of elementary operations performed by the algorithm differ by at most a constant factor. Since an algorithm's performance time may vary with different inputs of the same size, one commonly uses the worst-case time complexity of an algorithm, denoted as T, n, which is defined as the maximum amount of time taken on any input of size n. Time complexities are classified by the nature of the function T, n. For instance, an algorithm with T, n, equals O, n, is called a linear time algorithm, and an algorithm with T, n, equals O, 2n, is said to be an exponential time algorithm. Table of common time complexities. The following table summarizes some classes of commonly encountered time complexities. In the table, poly, x, a equals axo, 1, that is, polynomial and x. Constant time, an algorithm is said to be constant time if the value of t, n, is bounded by a value that does not depend on the size of the input. For example, accessing any single element in an array takes constant time as only one operation has to be performed to locate it. However, finding the minimal value in an unordered array is not a constant time operation, as a scan over each element in the array is needed in order to determine the minimal value. Hence it is a linear time operation, taking O, n, time. If the number of elements is known in advance and does not change, however, such an algorithm can still be said to run in constant time. Despite the name constant time, the running time does not have to be independent of the problem size, but an upper bound for the running time has to be bounded independently of the problem size. For example, the task exchange the values of A and B if necessary so that all per mille currency B is called constant time, even though the time may depend on whether or not it is already true that A per mille currency B. However, there is some constant t such that the time required is always at most t. Here are some examples of code fragments that run in constant time. Int index equals 5. Int item equals list, index. If then, perform some operation that runs in constant time, else, perform some other operation that runs in constant time, for I equals 1 to 100, for j equals 1 to 200, perform some operation that runs in constant time. If t, n, is O, any constant value, this is equivalent to and stated in standard notation as t, n, being O, 1. Logarithmic time. An algorithm is said to take logarithmic time if t, n, equals O, log n. Due to the use of the binary numeral system by computers, the logarithm is frequently base 2. However, by the change of base for logarithms, log n and log(n) differ only by a constant multiplier, which in big O notation is discarded. Thus O, log n, is the standard notation for logarithmic time algorithms regardless of the base of the logarithm. Algorithms taking logarithmic time are commonly found in operations on binary trees or when using binary search. An O, log n, algorithm is considered highly efficient, as the operations per instance required to complete decrease with each instance. A very simple example of this type of f, n, is an algorithm that cuts a string in half. It will take O, log n, time since we chop the string in half before each print. This means, in order to increase the number of prints, we have to double the length of the string. Polylogarithmic time. An algorithm is said to run in polylogarithmic time if t, n, equals O log n, k, for some constant k. For example, Matrix chain ordering can be solved in polylogarithmic time on a parallel random access machine. Sublinear time, an algorithm is said to run in sublinear time if t, n, equals O, n. In particular, this includes algorithms with the time complexities defined above, as well as others such as the O, now 1/2 Grover search algorithm. Typical algorithms that are exact and yet run in sublinear time use parallel processing, non-classical processing, or alternatively have guaranteed assumptions on the input structure. However, languages such as the set of all strings that have a 1 bit in the position indicated by the first log, n, bits of the string may depend on every bit of the input and yet be computable in sublinear time. The specific term sublinear time algorithm is usually reserved to algorithms that are unlike the above in that they are run over classical serial machine models and are not allowed prior assumptions on the input. They are however allowed to be randomized, and indeed must be randomized for all but the most trivial of tasks. As such, an algorithm must provide an answer without reading the entire input. Its particulars heavily depend on the access allowed to the input. Usually for an input that is represented as a binary string b1, bk, it is assumed that the algorithm can in time O1, request and obtain the value of b for any I. Sublinear time algorithms are typically randomized, and provide only approximate solutions. In fact, the property of a binary string having only zeros can be easily proved not to be decidable by a sublinear time algorithm. Sublinear time algorithms arise naturally in the investigation of property testing. Linear time, an algorithm is said to take linear time, or O, n, time, if its time complexity is O, n. Informally, this means that for large enough input sizes the running time increases linearly with the size of the input. For example, a procedure that adds up all elements of a list requires time proportional to the length of the list. This description is slightly inaccurate, since the running time can significantly deviate from a precise proportionality, especially for small values of n. Linear time is often viewed as a desirable attribute for an algorithm. Much research has been invested into creating algorithms exhibiting linear time or better. This research includes both software and hardware methods. In the case of hardware, some algorithms which, mathematically speaking, can never achieve linear time with standard computation models are able to run in linear time. There are several hardware technologies which exploit parallelism to provide this. An example is content-addressable memory. This concept of linear time is used in string matching algorithms such as the Boyer-Moore algorithm and Dirk-Cornyn's algorithm. Linearithmic time, a linearithmic function is a function of the form na log n. An algorithm is said to run in linearithmic time if t, n, equals O, and log n. Thus, a linearithmic term grows faster than a linear term but slower than any polynomial in n with exponents strictly greater than 1. In many cases, the na log n running time is simply the result of performing ai, log n, operation n times. For example, binary tree sort creates a binary tree by inserting each element of the n-sized array one by one. Since the insert operation on a self-balancing binary search tree takes O, log n, time, the entire algorithm takes linearithmic time. Comparison sorts require at least linearithmic number of comparisons in the worst case because log n equals I, and log n, by Stirling's approximation. They also frequently arise from the recurrence relation t, n, equals 2t, n/2, plus O, n. Some famous algorithms that run in linearithmic time include quicksort in the average case, heap sort, merge sort, intrasort, binary tree sort, smooth sort, patient sorting, etc. In the worst case, fast Fourier transforms, Munge calculation, quasi-linear time. A generalization of linearithmic time is quasi-linear time. An algorithm is said to run in quasi-linear time if t, n, equals O, n log kn, for any constant k. Linearithmic time is the case chi equals A1. Quasi-linear time algorithms are also O, n1 plus I micron for every I micron 0, and thus run faster than any polynomial in n with exponents strictly greater than 1. Algorithms which run in quasi-linear time, in addition to the linear-arithmic algorithms listed above, include in-place merge sort, O, and log2n, subquadratic time. An algorithm is said to be subquadratic time if t, n, equals O, n2. For example, most Norvay comparison-based sorting algorithms are quadratic, but more advanced algorithms can be found that are subquadratic. No general-purpose sorts run in linear time, but the change from quadratic to subquadratic is of great practical importance. Polynomial time. An algorithm is said to be of polynomial time if its running time is upper bounded by a polynomial expression in the size of the input for the algorithm, that is, t, n, equals O, nk, for some constant k. Problems for which a deterministic polynomial time algorithm exists belong to the complexity class P, which is central in the field of computational complexity theory. Cobham's thesis states that polynomial time is a synonym for tractable, feasible, efficient, or fast. Some examples of polynomial time algorithms: the quicksort sorting algorithm on n integers performs at most operations for some constant a. Thus it runs in time and is a polynomial time algorithm. All the basic arithmetic operations can be done in polynomial time. Maximum matchings in graphs can be found in polynomial time. Strongly and weakly polynomial time. In some contexts, especially in optimization, one differentiates between strongly polynomial time and weakly polynomial time algorithms. These two concepts are only relevant if the inputs to the algorithms consist of integers. Strongly polynomial time is defined in the arithmetic model of computation. In this model of computation, the basic arithmetic operations take a unit time step to perform, regardless of the sizes of the operands. The algorithm runs in strongly polynomial time if the number of operations in the arithmetic model of computation is bounded by a polynomial and the number of integers in the input's instance. And the space used by the algorithm is bounded by a polynomial and the size of the input. Any algorithm with these two properties can be converted to a polynomial time algorithm by replacing the arithmetic operations by suitable algorithms for performing the arithmetic operations on a Turing machine. If the second of the above requirement is not met, then this is not true anymore. Given the integer, it is possible to compute with n multiplications using repeated squaring. However, the space used to represent is proportional to, and thus exponential rather than polynomial in the space used to represent the input. Hence, it is not possible to carry out this computation in polynomial time on a Turing machine, but it is possible to compute it by polynomially many arithmetic operations. Conversely, there are algorithms which run in a number of Turing machine steps bounded by a polynomial in the length of binary encoded input, but do not take a number of arithmetic operations bounded by a polynomial in the number of input numbers. The Euclidean algorithm for computing the greatest common divisor of two integers is one example. Given two integers and the running time of the algorithm is bounded by Turing machine steps. This is polynomial in the size of a binary representation of, and as the size of such a representation is roughly. At the same time, the number of arithmetic operations cannot be bound by the number of integers in the input. Due to the latter observation, the algorithm does not run in strongly polynomial time. Its real running time depends on the magnitudes of and not only on the number of integers in the input. An algorithm which runs in polynomial time but which is not strongly polynomial is said to run in weakly polynomial time. A well-known example of a problem for which a weakly polynomial time algorithm is known, but is not known to admit a strongly polynomial time algorithm, is linear programming. Weakly polynomial time should not be confused with pseudo-polynomial time. Complexity classes. The concept of polynomial time leads to several complexity classes in computational complexity theory. Some important classes defined using polynomial time are the following. P. The complexity class of decision problems that can be solved on a deterministic Turing machine in polynomial time. NP. the complexity class of decision problems that can be solved on a non-deterministic Turing machine in polynomial time. ZPP, the complexity class of decision problems that can be solved with zero error on a probabilistic Turing machine in polynomial time. RP, the complexity class of decision problems that can be solved with one-sided error on a probabilistic Turing machine in polynomial time. BPP, the complexity class of decision problems that can be solved with two-sided error on a probabilistic Turing machine in polynomial time. BQP, the complexity class of decision problems that can be solved with two-sided error on a quantum Turing machine in polynomial time. P is the smallest time complexity class on a deterministic machine which is robust in terms of machine model changes. Any given abstract machine will have a complexity class corresponding to the problems which can be solved in polynomial time on that machine. Superpolynomial time. An algorithm is said to take superpolynomial time if t, n, is not bounded above by any polynomial. It is I per mil, nc, time for all constant c, where n is the input parameter, typically the number of bits in the input. For example, an algorithm that runs for 2n steps on an input of size n requires superpolynomial time. An algorithm that uses exponential resources is clearly superpolynomial, but some algorithms are only very weakly superpolynomial. For example, the Adler-Meynell Pomerance-Rumley primality test runs for no log n time on n-bit inputs. This grows faster than any polynomial for large enough n, but the input size must become impractically large before it cannot be dominated by a polynomial with small degree. An algorithm that requires superpolynomial time lies outside the complexity class P. Cobham's thesis posits that these algorithms are impractical, and in many cases they are. Since the P versus NP problem is unresolved, no algorithm for an NP-complete problem is currently known to run in polynomial time. Quasi-polynomial time. Quasi-polynomial time algorithms are algorithms which run slower than polynomial time, yet not so slow as to be exponential time. The worst-case running time of a quasi-polynomial time algorithm is for some fixed c. The best-known classical algorithm for integer factorization, the general number field sieve, which runs in time about is not quasi-polynomial since the running time cannot be expressed as for some fixed c. If the constant c in the definition of quasi-polynomial time algorithms is equal to 1, we get a polynomial time algorithm, and if it is less than 1, we get a sublinear time algorithm. Quasi-polynomial time algorithms typically arise in reductions from an NP-hard problem to another problem. For example, one can take an instance of an NP-hard problem, say 3SAT, and convert it to an instance of another problem B, but the size of the instance becomes. In that case, this reduction does not prove that problem B is NP-hard. This reduction only shows that there is no polynomial time algorithm for B unless there is a quasi-polynomial time algorithm for 3SAT. Similarly, there are some problems for which we know quasi-polynomial time algorithms, but no polynomial time algorithm is known. Such problems arise in approximation algorithms. A famous example is the directed Steiner tree problem, for which there is a quasi-polynomial time approximation algorithm achieving an approximation factor of, but showing the existence of such a polynomial time algorithm is an open problem. The complexity class QP consists of all problems which have quasi-polynomial time algorithms. It can be defined in terms of DTIME as follows. Relation to NP-complete problems. In complexity theory, the unsolved P versus NP problem asks if all problems in NP have polynomial time algorithms. All the best-known algorithms for NP-complete problems like 3SAT etc. take exponential time. Indeed, it is conjectured for many natural NP-complete problems that they do not have sub-exponential time algorithms. Here sub-exponential time is taken to mean the second definition presented below. This conjecture is known as the exponential time hypothesis. Since it is conjectured that NP-complete problems do not have quasi-polynomial time algorithms, Some inapproximability results in the field of approximation algorithms make the assumption that NP-complete problems do not have quasi-polynomial time algorithms. For example, see the known inapproximability results for the set cover problem. Sub-exponential time. The term sub-exponential time is used to express that the running time of some algorithm may grow faster than any polynomial but is still significantly smaller than an exponential. In this sense, problems that have sub-exponential time algorithms are somewhat more tractable than those that only have exponential algorithms. The precise definition of sub-exponential is not generally agreed upon, and we list the two most widely used ones below. First definition: a problem is said to be sub-exponential time solvable if it can be solved in running times whose logarithms grow smaller than any given polynomial. More precisely, a problem is in sub-exponential time if for every I micro AA0 there exists an algorithm which solves the problem in time 0.2 micron. The set of all such problems is the complexity class SUBEXP, which can be defined in terms of DTIME as follows. Note that this notion of sub-exponential is non-uniform in terms of I micron in the sense that I micron is not part of the input and each I micron may have its own algorithm for the problem. Second definition: some authors define sub-exponential time as running times in 2O(n). This definition allows larger running times than the first definition of sub-exponential time. An example of such a sub-exponential time algorithm is the best-known classical algorithm for integer factorization, the general number field sieve, which runs in time about, where the length of the inputs is n. Another example is the best-known algorithm for the graph isomorphism problem, which runs in time 2O, h, now log n. Note that it makes a difference whether the algorithm is allowed to be sub-exponential in the size of the instance, the number of vertices, or the number of edges. In parameterized complexity, this difference is made explicit by considering pairs of decision problems and parameters k. Sub-ept is the class of all parameterized problems that run in time sub-exponential in k and polynomial in the input size n. More precisely, sub-ept is the class of all parameterized problems for which there is a computable function with and an algorithm that decides L in time. Exponential time hypothesis. The exponential time hypothesis is that 3SAT, the satisfiability problem of Boolean formulas in conjunctive normal form with at most 3 literals per clause and with n variables, cannot be solved in time 2O(n). More precisely, the hypothesis is that there is some absolute constant c greater than 0 such that 3SAT cannot be decided in time 2Cn by any deterministic Turing machine. With m denoting the number of clauses, ETH is equivalent to the hypothesis that KSAT cannot be solved in time 2O(m), for any integer k permel beta 3. The exponential time hypothesis implies PA permel NP. Exponential time. An algorithm is said to be exponential time, if t, n, is upper bounded by 2 poly, n, where poly, n, is some polynomial and n. More formally, an algorithm is exponential time if t, n, is bounded by O, 2nk, for some constant k. Problems which admit exponential time algorithms on a deterministic Turing machine form the complexity class known as exp. Sometimes, exponential time is used to refer to algorithms that have t, n, equals 2O(n), where the exponent is at most a linear function of n. This gives rise to the complexity class E. Double exponential time. An algorithm is said to be double exponential time if t, n, is upper bounded by 22 poly, n, where poly, n, is some polynomial and n. Such algorithms belong to the complexity class 2x-time. Well-known double exponential time algorithms include, decision procedures for Presburger arithmetic, computing a gra-paragraph BNER basis, quantifier elimination on real closed fields takes at least double exponential time, see also, L notation, references.